Hello, spaghetti monsters. It's Mr. Spinelli. Today we're going to look at a few problems involving position, velocity, and acceleration, and then we're going to look at a few optimization problems. So first, PVA. We've got a particle moving. Its position is given by the function x of t, so it's moving along the x-axis, and we're going to use this to answer a few questions. So the first thing we want to compute is the displacement of the particle in the first 7 seconds. So when we want to find displacement, we just need to figure out how far it is from its original position. So we're going to compute x of 7 minus x of 0. I trust you can plug those values in. You end up with 217 minus 0. I'm going to give this units. We're going to say the position is in meters and the time is in seconds. So my displacement will be equal to 217 meters. So be sure to pay attention to the units that the problem gives you. Displacement should be in units of length. Okay. Next question says average velocity. So keyword is average here. And we want the average velocity in the first 4 seconds. So we just need to compute the slope between the position at time t equals 0 and time t equals 4. So that's going to be done by computing x of 4 minus x of 0 over 4 minus 0. Plugging that in, we get 16 minus 0 over 4. We end up with 4. And the units for velocity are going to be meters per second. Recall, if we've got position given by x of t, then velocity is going to be given by x prime of t, and acceleration will be given by x double prime of t, or v prime of t. And the units for these are going to be length, length per time, and length per time squared, respectively. So I'll put those in brackets so you know that that is referencing the units of position, velocity, and acceleration, respectively. But when we're computing average velocity, like we did in this part B, we need to just compute the slope of the position function between the starting and ending points. Next problem asks about instantaneous velocity. When you see instantaneous, you need to think derivative. So I actually need to compute v of t, which is equal to x prime of t. So in taking my derivative of my original function, I get 3t squared minus 4t minus 4. Now I need to evaluate that at 2. So I trust that you can plug in 2, and you'll find that you get 0 meters per second. Okay. Next problem asks us to compute average acceleration. So for average acceleration, I need to be looking at my velocity function and the slope between the starting and ending points. So v of 4, because it's the first 4 seconds, minus v of 0 over 4 minus 0. So I trust that you can go back up to this function that we just found here. Okay, that was our velocity function. We're going to plug in 4 and then plug in 0. So we end up with 28 minus negative 4 over 4. So we end up with 32 over 4, or 8. And the units for acceleration are meters per second squared. So again, you see average, think slope. You see instantaneous, think derivative. So again, I've got my function here, x of t, written again for you in case you forgot it. So I'm going to take the derivative of v prime of t, the derivative of v of t to get my acceleration, which is just my second derivative of this original position function. So doing that, I get 6t minus 4. Since I want to compute that at a particular point, I plug in 2, get 12 minus 4 is 8 meters per second squared. Okay, so moving on, these are the fun questions you're going to run into on the AP tests. On what intervals is the particle moving right or left? So in order to determine when it's moving right, I need to find when v of t is positive. To find when it's moving left, I need to find when v of t is negative. So going back to my velocity function that I'd computed from my first derivative, I get that in factored form, it's 3t plus 2 and t minus 2. So I want to set this velocity equal to 0, and in doing so, I get t equals negative 2/3 and t equals 2. So I'm going to make a sign chart with values for t of negative 2/3 and 2. So plugging a number to the left, to the right of these numbers, I can create a sign chart. Or if you notice, this is a parabola opening up with zeros of negative 2/3 and 2. You know that it's below, in between those, and above the x-axis on the outside. Again, either way works. Use your intuition of what you know about parabolas, and you can make sign charts even quicker. So when is it moving to the right? Well, it's moving to the right for negative infinity to negative 2/3 and 2 to infinity. And I might have gone just outside the margins. And it's moving to the left in between negative 2/3 and 2. Alright. Next one says, when is the particle furthest to the right on the interval negative 1 to 4? So ultimately, I would want to find my critical numbers for velocity, which I just did, negative 2/3 and 2. Remember, critical numbers are where your derivative is 0 or undefined. So I need to plug in those critical numbers that fall within that interval, negative 1 to 4, which in this case is both of them. So I'm going to compute x of negative 1, x of 4. Those are my endpoints. So I'm plugging these t values into my original function, which again I have written up here, x of t equals t cubed minus 2t squared minus 4t. I'm going to plug in the endpoints. When I do that, I get 1 and 16. And then I'm also going to plug in the critical numbers I got from before. Now, I should be expecting something further to the right at negative 2/3 and something further to the left at positive 2. And that's just based on this sign chart. So that's going to the right and this one's going to the left. So I should notice that. But it may not be further right or left than my endpoints. So when I plug negative 2/3 in, I get 40 over 27, which is equal to 1.48148. That 148 repeats forever. And then when I plug in 2, I get negative 8. So when is it furthest to the right? Well, I need to determine which of these values is the biggest, and that's 16. So it's furthest to the right when t equals 4. Furthest to the left, I need to look for my smallest number, and that's negative 8. So that's when t equals 2. So this question says when. So that's why I'm giving answers in terms of time. If it said how far, when it was the furthest to the left or the right, then I would provide that distance, and these distances would be in meters. Whereas my time is in seconds. Now the next question says, on what intervals is the particle speeding up and slowing down? So this is where I need to find acceleration and compare the signs of velocity and acceleration. So in taking my derivative of the velocity equation, I end up with 2 times 3t minus 2 in factored form. Set that equal to 0, I get t equals 2/3. So t equals 2/3 is my critical number for the acceleration. When I make my sign chart, I'm going to put velocity on the bottom and acceleration up here. So I've got my negative 2/3 and my 2 for my critical numbers of my velocity function. And then for my acceleration function, I just found a critical number of 2/3. So this one here is t equals 2/3. I already know this one goes positive, negative, positive for velocity. Plug a number to the left of 2/3 and I get a negative, and to the right I get a positive. So if we were to look when this thing is speeding up, I'll highlight those sections in green. Speeding up is when the signs are the same. So that's going to happen when velocity and acceleration are both negative, and when velocity and acceleration are both positive. So speeding up, I'm just going to use an up symbol because you're paying attention and you know what I'm doing. Speeding up from negative 2/3 to positive 2/3. So that's that first green highlighted section. And then from 2 on to infinity. Slowing down is everywhere else. I'll go ahead and highlight that in red for you. So that's where I am opposite. So here I've got negative acceleration, positive velocity. Here I've got positive acceleration and negative velocity. So I'm slowing down from negative infinity to negative 2/3, and from 2/3 to 2. So some good concepts covered here. Make sure you review and slow down as needed. So now we'll dive into the optimization problems. This first one I wouldn't really expect you to see on the AP test because I don't know that they're going to use this phrase geometric mean. But I wanted to throw that at you just so you are familiar with it. Geometric mean, you take the nth root of the product of the n numbers. So since we have 3 numbers, you can think of them as x, y, z. I'll go ahead and write x, y, z for you. So those are the 3 numbers we're going to use. I'm actually going to change one of them after we read the second part of this sentence. So if we multiply those 3 numbers together and then take the cubed root, since there's 3 numbers, that would be the geometric mean. So this has to be equal to 3. So a lot of 3's. This 3 is purely coincidental, but it's going there. The 3 right here is because we're doing the geometric mean of 3 numbers. So the next part of it says that one of the numbers is twice as big as one of the others. So instead of z, I'm going to say z is twice x. So I've got x, y, and 2x. So if I replace that statement, I've now got 2x squared times y. And that all has to equal 3. Alright, so ultimately though, what do I want to do? It says I need to find the sum of the 3 numbers such that it is a minimum. So I like to write what I'm trying to minimize. So I'm trying to minimize a sum. So I'm adding things together, so I'm just going to use an a. Right now I've got a of x comma y. It's a function of 2 variables. I'm going to be adding x, the y, and the 2x. Those are my 3 numbers that I'm adding together. But this is calculus of a single variable, so I don't know how to take derivatives when my function has 2 variables. I know how to do it implicitly, but I haven't yet learned partial derivatives, and you won't learn that till Calc 3. So I need to get this function a of xy in terms of just a single variable. So in order to do that, I'm going to take my constraint, this whole geometric mean equals 3, and I'm going to solve that equation for x or y. It does not make a difference, but in some cases it's easier to solve for one variable than the other. In this case, it's easier to solve for y. You cube both sides and you get 2x squared y equals 27. 3 cubed is 27. Divide both sides by 2x squared and you get y equals 27 over 2x squared. So I'm going to replace that in my function. So then I will have a function of only x. Now I'm going to go ahead and combine the x and the 2x to make 3x. And then I'm replacing y with 27 over 2x squared. So again, that's coming from here. Y equals 27 over 2x squared, making that substitution. Now I'm ready to take my derivatives, set it equal to 0, find my critical numbers, make a sign chart, all the things you will do in every single optimization problem. So the goal is get a problem where you have an equation in terms of one variable, take your derivatives, set it equal to 0, get your critical numbers, find out which ones are maxes and mins, etc., and make sure your number makes sense in the end. So taking the derivative of this, a prime of x, I end up with 3 minus 54 over x cubed. I'll let you pause the video if necessary to figure out how I got that simplified so quickly, and I need to set that equal to 0. Now, I'm not going to spend too much time on the algebra of this, but you should end up with x cubed equals 18. Okay, I wanted this part right here to be equal to 18, so I know the bottom has to be equal to 3, so I know the bottom has to be 18. Then cubed rooting, I get x equals the cubed root of 18. Now I should make a sign chart, but if you're familiar with this type of function, you should know how it's going to look. So I'm going to make a sign chart, cubed root of 18, plug something to the left. I'm going to plug in 0, but I can't because that's undefined, so I'll just plug in 1. 54 over 1 is positive, but 3 minus that is going to be negative. And then plug something into the right, it's positive, so I know that my original function is decreasing and then increasing, so I know that I've got the minimum. So it says find the 3 numbers, so I've got x's cube root of 18, so I'm going to go back to this original statement and plug x in. So I've got cubed root of 18. I know one of them is twice as big, so I've got 2 times the cube root of 18. So that takes care of the x and the 2x. And then I finally need to plug x into what I had said y is equal to from my constraint function. And if I do that, I get 27 over 2 times the cubed root of 18 squared. So those are my 3 numbers whose geometric mean is 3 and whose sum is a minimum. Alright, so let's take a look at the next one. This is a standard problem you will see on many calc texts, examples online, etc. So we've got a rectangular plot of farmland will be bounded on one side by a river and on the other 3 sides by a single strand electric fence. And then this area will be further divided into 3 equally sized areas. So we've got 500 meters of fencing. What is the largest area you can enclose? Pretend there's an A after the R. What's the largest area you can enclose and what are the dimensions? So we've got 2 things we need to answer, the largest area and the largest dimensions. So we draw a picture, here's my nice little river. We're going to build a rectangular fence and then we're going to further divide it into 3 equal pieces. So all the fence, let me actually do that in a different color. Let me highlight that in green. All my fence is going to be here. The rest is river. Now, what are the dimensions? I like to use x and y. So if I call this length x and this length y, I've actually got the length x 4 times. So when I'm computing my perimeter, which is ultimately how I'm going to use this 500 meters, when I'm computing my perimeter, 500 is going to have to equal the 4 x's and the y, the sum of those. So this is my constraint. I'm ultimately going to solve this for either x or y. The thing that I want to maximize is the area. So right now my area is in terms of x and y, and it's just simply x times y, area of a rectangle. But I'm going to solve this equation for y, because y has a coefficient of 1, which makes my life easy. So 500 minus 4x, and I'm going to substitute that in to my area function so that my area is only a function of one variable, in this case x. So I've got x times 500 minus 4x. Distributing, I get 500x minus 4x squared. Alright, so now got my function in terms of one variable only. I'm ready to do the usual. Take the derivative, set it equal to 0, find the critical numbers, and determine if they're maxes, because I want a max for this problem. So taking my derivative, a prime of x, I get 500 minus 8x. Setting that equal to 0, I get x equals 500 over 8, which simplifies to 125 over 2, or 62.5 for those of you that prefer decimals. Now, recalling that I said that y is equal to 500 minus 4x, I'm going to plug that x value in. So I get y equals 500 minus 4 times 125 over 2. Simplifying that, I get 250. Now these are all in units of meters, so I'm going to indicate that with meters. Now I should make a sign chart, but I really shouldn't have to. You guys should know that this is a parabola that opens down, so you know that the critical number you find is going to be a maximum. So save your energy on sign charts when you know you don't have to make one. So it asks for the largest area and the dimensions. So my dimensions are simply 125 over 2, or 62.5 meters by 250 meters. And if I multiply those together, I get an area of 125 cubed meters squared, or 15,625 meters squared. So that's the same as 5 to the 6th, or 125 to the 2nd. All right, next problem. Here's a fun one. This is a more realistic type problem. If you get into manufacturing or maybe some type of engineering, perhaps a manufacturing engineering, or drawing a blank. Industrial engineering is where you might see these types of problems. So Orange Cow is designing a can for their newest energy drink. The right cylinder can, I'm going to highlight that, right cylinder can, is to contain 600 centimeters cubed of their putrid potion. The cost of the material for the top and bottom, top and bottom of the can is this small number, dollars per centimeter squared. So I need to multiply area by that number to get the actual cost for that material. And then the cost for the sides, we'll do that in green, material for the sides is this other very small number. Now, they want to minimize the costs, which makes sense. They want to make the most bang for their buck. So they want to minimize the costs, so we need to find the dimensions of the can. So I'm going to start with this first thing here, the right cylinder can and the volume. So I need to know that the volume of a can is pi r squared h for the cylinder. So here's my very, very crude sketch. You can find better pictures online. There's my h and there's my r. Okay, so there's my can. Volume is pi r squared h. That has to equal 600. Now looking at this right away, I'm going to solve that equation for h because I know I need to have a function in terms of one variable. H is easier to solve for. I get 600 over pi r squared. Now, if I look at my surface areas, so I've got surface area for my top and bottom, and surface area for my sides. Top and bottom, you've got a circle. Area of a circle is pi r squared, but you've got two of them, so 2 pi r squared. Area for the sides is basically the circumference of the circle times the height. Circumference is 2 pi r, so I get 2 pi r h, but I'm going to go ahead and replace h with 600 over pi r squared, because that's the value I got from my constraint function. I have to make a can that has 600 centimeters cubed of liquid, which for those wondering is actually 0.6 liters. So then, that's the surface area, so now I need to multiply those by the respective costs. So then the cost, I'll actually use a C instead of an S. The cost for the top and bottom is the 0.00025. For the sides, that 25 becomes 15. Right, so usually that material on the top and bottom is a little sturdier than on the side, so it's a little more expensive to produce. All right, so then what is the ultimate cost? Well, I've got to multiply these numbers together and these numbers together, and then add that result to get my cost function. In this case, my cost function will be in terms of R. So my cost function in terms of R, again, this is with simplification, multiplying these out. You should be able to do that. Check your work with mine. You should get 0.005 pi r squared plus 0.18 r to the negative first. Okay, I'm writing it with the negative exponents because I know I'm going to be taking the derivative and setting it equal to 0, which is my next step. So c prime of r is equal to 0.001 pi r minus 0.18 r to the negative second. Now I want to set this equal to 0. So if you haven't watched my factoring video and you still aren't comfortable with factoring, you should do so. But I'm going to factor out r to the negative second. Then on the inside I'll have 0.001 pi r cubed minus 0.18 equal to 0. So you should recognize that this r to the negative second is just going to move r to the bottom, which means r can't be 0. That makes sense. We can't even make a can if the radius were 0. So ultimately I need to set this part inside the parentheses equal to 0. And when I do that, which again I will invite you to check your work, you should get the cubed root of 0.18 over 0.001 pi. Okay, I am not doing any simplification for the sake of your sanity and mine. And then if I plug that in to this h equation, the equation for h that I got from my constraint, you will find that h equals 600 over pi times that thing squared. Now, ultimately, this would probably be a calculator problem. So what is the actual radius and height and cost of the can? Well, the radius is 3.855 centimeters. The height would be 12.85 centimeters. And the cost, so cost, plugging in 3.855 into this function right here, I would get a cost of about 7 cents. Okay? So I've used my constraint, solved it for h, plugged that in for h for the area of the sides, for that surface area, which was 2 pi r times the h, computed the cost by multiplying the areas by the cost for the respective material, added those up, take the derivative, set it equal to 0, and find my critical point. Again, I should have made a sign chart, but again, I'm familiar with what these functions look like, so I knew that I had a minimum. I shouldn't assume that though, and you shouldn't either. Alright, next problem, very common one. Should be able to get this pretty quickly. We've got a rectangle whose base is on the x-axis and its upper two vertices are on the parabola 20 minus x squared. I want to compute the largest area and determine its dimensions. So, if I draw a very crude sketch, parabola goes up to 20. Okay, so this is going to come over to negative root 20 and over to positive root 20, and it's going to go up to 20. Now I'm going to just assume some rectangle so I can dimension it. So there's the rectangle I would get. Now, as I move this direction, I'm x over. I'm just over x units to the right, which means I'm also x units to the left. So the base has an overall dimension of 2x. Now the question is, what is my height? Well, my height is simply given by the function, which is 20 minus x squared. So then the area of this particular rectangle in terms of x is going to be 2x times 20 minus x squared. This is a very common problem. Your height of whatever shape you decide to put in here is usually given by the function, which in this case is a parabola. So if I simplify this by distributing, I get 40x minus 2x cubed, and now I'm ready to take my derivative and set it equal to 0. A prime of x is 40 minus 6x squared. This should be pretty straightforward to solve. You should end up with x squared equals 40 over 6, or 20 over 3. So then if you square root both sides, you get plus or minus 20 thirds. We're just going to go with the positive one because we understand that this is a symmetric problem, and we should take the positive one because when we refer to dimensions, we should also refer to positive lengths, because we won't refer to negative lengths when we measure something. I challenge you to find a ruler with negative numbers on it. Now, going back to the substitution we made, y equals 20 minus x squared with the equation of that parabola, we get y equals 20 minus 20 thirds. Right? So here's the x squared. I'm just plugging this right into here. So 60 thirds minus 20 thirds is 40 thirds. So we answer the question of dimensions. What are the dimensions of my rectangle? It is root 20 thirds by 40 thirds. Now you could simplify the root 20 thirds. Write 20 as 5 times 4. Square root of 4 is 2, so you could write it as 2 root 5 over 3. I'm not going to waste my time doing that. Depends on if this were a multiple choice, what kind of answer would you expect to see? Be on the lookout for that. And then if I compute the area, I just need to multiply these two numbers together, and I end up with 40 root 20 over 3 root 3. Again, you can simplify that and make sure it looks like what the AP test has if this is a multiple choice question. Alright, so finally, the last problem. Ooh, good luck reading this one. Alright, this is one of my favorites. A 100-meter piece, or 100 centimeter. Let's see if I can scroll up and find it again. Alright, a 100 centimeter piece of wire is cut into two pieces. One piece is bent into a circle, and the other is bent into a square. So I made this one kind of easy with the square. You might see ones with equilateral triangles or rectangles, so be on the lookout for those. Give those a try. I want to determine where, if anywhere, the wire should be cut to maximize the area. So I'm going to start with a piece of wire, and I'm going to cut it here. I don't know where that is, and I could technically swap where the x and the 100 minus x are, but I know the entire length is 100, so I know if I cut something x units long, the other piece will be 100 minus x. Now, here's where you have options in terms of where you can go with which piece. I'm going to turn the left piece into a square because I think it's going to be easier to work with 100 minus x being the perimeter of my square versus x being the circumference of my circle. So you have to think about what these pieces of wire become. They become your perimeter. So perimeter of your triangle, your square, your rectangle, whatever shapes it's cutting into, these pieces become our perimeter, which in the case of a circle is circumference. So circumference we write as 2 pi r. So that will be equal to the length of x that I took from that wire. Now ultimately, I'm going to want to have everything in terms of x. So I'm going to write r equals x over 2 pi. Okay, this is going to be key. I'm going to box it. And I don't know what just happened there, so I'm going to try to box it again. And I'm going to leave it alone. There we go. So now, perimeter. My sides of my square are going to have some length y for each of the sides. So then the perimeter is simply 4y, and that has to equal the 100 minus x centimeters of wire that I cut to turn into a square. Now, like I said, I'm going to solve this for y. So y is simply 100 minus x over 4. So now both of my variables are in terms of x. Now the question is, how do I find the area? Well, the area for my square is simply y squared, which is 100 minus x over 4. squared. The area of my circle is pi r squared. So I've got pi r, which is x over 2 pi, squared. So again, this came from my square, and this was the area of my circle. Now, if I rewrite this just a little bit, and I'm not going to do a whole lot of rewriting because this one works out fairly nicely, I'm actually going to leave this one alone. I'm not going to actually square that polynomial, but I am going to rewrite this as 1 over 4 pi x squared. Again, you should check the simplification of that. Now I'm ready to take my derivative, set it equal to 0. So a prime of x. First one I'm going to use chain rule. 2 times this quantity. This quantity remains unchanged on the inside. Power drops down 1. Derivative of the inside is negative 1/4. I've got a negative in front of that x and a constant 4 on bottom. Derivative of my second term, multiply by 2, so the 4 pi on bottom becomes 2 pi, and the power of the x drops down 1. Now, little rewrite. This bottom on the first term is 16, but times the 2 just becomes 8. So then I get x minus 100 over 8 plus x over 2 pi. If I rewrite that, I end up with simply 2 pi x minus 200 pi, so I'm multiplying that first term by the denominator of the second term, plus 8x, and then my common denominator becomes 16 pi. So I want to set this equal to 0. So when I set this equal to 0, I'm going to factor out my x's. So maybe I should take some time, or I think you should challenge yourself to see how I got to this point. 2 pi plus 8 over 16 pi. That all gets multiplied by x and has to equal 200 over 16. So ultimately, I took this piece right here, added it to the other side, the pi's cancel out, and then I factored what remained on the left. So if you solve this, this is a fun practice. This is kind of a Algebra 2 pre-calc question maybe. Multiply by the reciprocal that I was trying to divide by. You simplify that, you get x equals 100 pi over pi plus 4. If you got a calculator on you, you can find out what that simplifies to and figure out where you need to cut along the wire. Don't know why I didn't do that beforehand, and I don't have a calculator anywhere near me, and I don't want to ruin this video by doing anything crazy. So there is your answer. And if you see two answers, maybe the other answer is not just x, but maybe 100 minus x. Because whether you're cutting from the left or the right, that x dimension, it doesn't really matter. So I hope this helped you. Good luck, and thank you for watching Merch to the Cap.